Hello, AP Chemistry students. This is Mrs. Altman. We are on video number 26, Chemical Equilibrium Part 2. Here are our objectives for today's video. Pause here. So an icebox problem is typically what you are going to do if you are looking for equilibrium concentrations. Sometimes you will also use it to determine the equilibrium constant, but that's not really what this video is about. We're just going to focus on getting concentrations in this video. Before you can do the problem, you need to determine what direction the reaction is going to proceed. If K is equal to Q, there is not going to be any reaction. The problem's done, nothing to solve. If Q is greater to K, the reaction will shift to the left, meaning that I'm going to be increasing my reactants, decreasing my products. And if Q is less than K, the equilibrium will shift, or the reaction will shift to the right, meaning we're producing more products and we're getting rid of some reactants. Let's take a look at an example of this. Pause here. So I'm going to walk you through this, but what I really want you to get out of this is not so much how to do the math, because I'm going to show you a simpler way to do it in class, but just how to set up the problem. So let's get to that. So we have a reaction and we have a value for K. I need to first determine what way the direction is going to be going. So to do that, I'm going to write out my equilibrium expression. So now that I have that, I can use that to determine Q. It says right in the question that all the concentrations are 2.0 to begin with. So my Q is equal to 1. That's a lot less than K. That means I'm going to be producing more products and getting rid of reactants. Now I'll get to actually doing the problem. So icebox just meaning I'm making a box. I've got a column for each reactant or product, and then I've got 3 rows, one for initial, one for change, one for equilibrium. So all of these are initially at 2.00. Now that I solve for Q, I know that I'm going to be producing products. So I'm going to be getting rid of some of this H2. I don't know how much. I'm going to call it X. I'm going to be getting rid of the same amount of Br2 since it's a 1-to-1 mole ratio. And then I'm going to be producing some quantity of HBr. So that's going to be plus 2X because of the fact of the 2 in front of it in the balanced chemical equation. So I'm not really going to be worrying about sig figs for these problems. That's why I did 2 minus X, and then 2 plus 2X. So now comes the part that I don't want you to worry about so much because I'm going to show you a simplified version of it, but I'll show you a little bit of this here. So we know that the equilibrium constant is equal to 62.5. And I get this problem. I've actually already gone ahead and solved this. I'll scroll down so you can see that. So what I did is I just turned this into a quadratic equation, and you don't need to write this all down, by the way. I want to show you what you would do at the end, and typically the numbers tend to work out pretty nicely, but since I can't take a problem directly from your book, it didn't really work out this way. I want to show you how we'd solve this. You're perfectly allowed to use a quadratic formula calculator. I highly encourage you to have one in your calculator. So I'm just going to go ahead and plug everything in. So you'll get 2 values. So I've got 1.39429, and I've got 3.01597. I want to point out that the second one right here is impossible, so I'm just going to throw it away. So typically you're going to get one answer that's impossible, and you just don't use that one. So I'm only going to use my one solution that's actually real, which is 1.39 molar. So then if I want to know my actual expressions, I end up getting 0.61 molar for my reactants and 4.78 for my products. Pause here. Right, so Le Chatelier's principle is just a way to think about how a reaction or an equilibrium will change. So if a system can stay at equilibrium, they typically will. It's the most thermodynamically stable position for something to be in. So it's just, how is that going to happen? Pause here. I'm going to give you like 15 seconds to think about it, and then I'm going to show the answers on the next slide and explain them. Okay, so if I increase the concentration of the reactant, I'm going to shift to the right. I'm going to be producing more product. That makes sense because otherwise I would no longer be at equilibrium. And then the reverse of that is also true. If I increase the concentration of the product, the equilibrium is going to shift to the left. If you increase pressure by adding an inert gas, there's not going to be an effect. The reason for that is because there's not actually any change to the number of collisions, because the inert gas, even if you're increasing the pressure, that inert gas isn't actually contributing to the collisions that affect the reaction rates. Adding heat, if you have an endothermic reaction, that means that heat is a reactant. Therefore, you're adding a reactant, and therefore it will shift to the right. Then the opposite is true. If you add heat to an exothermic reaction, heat is a product of an exothermic reaction. Therefore, you're adding a product, and there will be a shift to the left. Okay, here are the practice problems for today's video. Thank you so much for watching, and have a great night.